Okay, so we have electricity and magnetism practice final exam. Let's begin. So number one, a charge distribution consists of of a point charge plus Q at Z equals A and a point charge negative Q at Z equals negative A. For A, B, C, and D, find the electric potential V of R theta for R is greater than A. Show that the leading far field term is dipolar. Find the dipole moment vector P. Find the approximate electric field for R is much greater than A. And I'm just going to go through these rather quickly so you have these as a reference. Some of the computational steps and the intermediary steps are not going to be shown. So let's begin. Electrostatics and superposition problem. So charges plus Q at Z equals A, negative Q at Z equals negative A. So for R is greater than A, V is going to equal 1 over 4 pi epsilon naught times the quantity Q over magnitude of the difference between R and AZ hat minus Q over the magnitude of the sum of R and AZ hat. For R is much greater than A, V approximates 1 over 4 pi epsilon naught times 2QA cosine theta over R squared. So the dipole moment is 2Q AZ hat, and V approximates 1 over 4 pi epsilon naught times the dot product of the dipole moment and R hat over R squared. And the far field electric field is going to be E equals 1 over 4 pi epsilon naught times 1 over R cubed times the quantity 2p cosine theta R hat plus p sine theta theta hat. Okay, so that is number one. Let's go now to number two. Sorry, see if this holds up. Whoops. Sorry about that. Might as well just change it. So number two. Okay. So number two here, a solid insulating sphere of radius r has charge density given here. Rho of r equals rho naught times the quantity 1 minus r squared over r squared for r is greater than, lowercase r is greater than or equal to r, and rho equals 0 for r is greater than r. So for part A, find the total charge, Q. So this is a Gauss's law and non-uniform charge density problem. So finding the total charge here, the non-uniform charge sphere, we have for letter A, rho of r is rho naught times the quantity 1 minus r squared over r squared. Total charge, Q equals 0 to r. This integral, 0 to r, rho of r, 4 pi r squared dr. So again, integrating here, our Q is going to be 4 pi rho naught times this quantity r cubed over 3 minus r cubed over 5. And Q is going to equal 8 pi over 15 rho naught r cubed. Some of the intermediary steps not shown, but that's after the integration. That's what the Q yields. For r is less than capital R, our Q sub E and C, our enclosed is 4 pi rho naught quantity lowercase r cubed over 3 minus lowercase r to the 5th over 5 uppercase r squared. Okay, and from Gauss's law, E of 4 pi r squared, that's going to equal Q sub E and C over epsilon naught. Okay, for part B here, our E of R, that's going to be rho over E epsilon naught times the quantity r over 3 minus r cubed over 5 capital R squared. For r is greater than capital R, E of r is 1 over 4 pi epsilon naught times Q over r squared. And my apologies for misspelling this. This should be maximum. My apologies for the misspelling. Maximum inside. We find the derivative of v with respect to r, set it equal to 0. So that's going to be 1/3 minus 3r squared over 5 capital R squared equals 0, or r equals capital R square root of 5 over 9. So r is going to be equal to square root of 5 over 3 capital R. So that's for number 2. And now moving along to number 3. Okay, so number 3, sorry about that. Okay, number 3, a neutral conducting spherical shell. Okay, here has inner radius and outer radius B. A point charge plus Q is placed at the exact center of the hollow cavity. Okay, so let's see what we have here. Conductors and boundary conditions. Part A, find the charge induced on the inner surface. Part B, find the charge induced on the outer surface. Part C, find E of R in all regions. R is greater than A is less than R is less than B. R is greater than B. Find the potential everywhere, taking V of infinity equals 0, and explain why the field inside the conducting material is 0. Okay, so conductors and boundary conditions problem. Conducting spherical shell, point charge plus Q at the center. So the induced charge on the surface is going to be negative Q. So the outer surface must have positive Q. For our fields, R less than A, E is 1 over 4 pi epsilon naught times Q over R squared. And for A is less than R is less than B, E equals 0. And for R is greater than B, well, E is going to equal 1 over 4 pi epsilon naught Q over R squared. Okay. For part D, the potential with V of infinity equals 0. So for R is greater than B, V equals 1 over 4 pi epsilon naught times Q over R. For A is less than R is less than B, V equals 1 over 4 pi epsilon naught times Q over B. And for R is less than A, V equals 1 over 4 pi epsilon naught times this quantity, Q over R minus Q over A plus Q over B. In part E, the field inside the conductor is 0 because free charges rearrange with electrostatic equilibrium because free charges rearrange until electrostatic equilibrium is reached. Okay, so that takes care of number 3. Moving along now to number 4. Okay, number 4. Let's see. A point charge Q is located a distance d above an infinite grounded conducting plane. Part A, find the image configuration. Part B, find the potential in the region above the plane. C, find the force on the real charge. D, find the induced surface charge density, sigma of xy, on the plane. Show that the total induced charge is negative Q. So method of images problem. So the image charge is negative Q. Located distance d below the plane for z is greater than 0. So V is going to be equal to 1 over 4 pi epsilon naught times this whole quantity, Q over square root of x squared plus y squared plus the difference between z and d squared minus Q over the square root of the quantity x squared plus y squared plus the sum of the quantity z plus d, sum of z and d squared. Force on real charge equals force from image charge. So F is going to equal negative 1 over 4 pi epsilon naught Q squared over the quantity 2d squared z hat. And F is going to equal negative Q over 16 pi epsilon naught d squared z hat. For our surface charge density, sigma is negative E naught. And then you have the partial derivative dv dz, v with respect to z, evaluated at z equals 0. Our surface, our sigma of our value here is going to be equal to negative qd over this 2 pi plus this quantity here, where our rho is our square root of x squared plus y squared. So our total induced charge is going to be Q sub IND is the integral from 0 to pi sigma 2 pi rho d rho, and that's going to equal to negative Q. Okay, so that's for number 4. Moving along to number 5. Okay. Moving along to number 5. So potential of the surface of a sphere, radius r, is V of r theta equals V naught cosine squared theta. There is no charge inside or outside the sphere. Okay, for A, find the potential inside the sphere. For B, find the potential outside the sphere, assuming V approaching 0 or r approaching infinity. C, find the surface charge density on the sphere if it is a conducting shell held at this potential. Okay, so this is a Laplace's equation in spherical coordinates problem. We're going to use cosine squared theta equals 1/3 plus 2/3 p sub 2 cosine theta. So inside V sub n, that's going to equal a naught plus a sub 2 r squared p sub 2 cosine theta. And at lowercase r equals capital R, V sub n equals V naught over 3 plus 2 V naught over 3 plus r squared over capital R squared p sub 2 cosine theta. And outside, V sub out is P naught over B naught over R plus B sub 2 over R cubed, P sub 2 cosine theta. So V sub out is V naught R over 3R plus 2V naught capital R cubed over 3R cubed times P sub 2 cosine theta. And moving along to our surface charge density, sigma equals epsilon naught times this quantity, E sub out minus E sub in, dotted with R hat. So our sigma of theta is E naught, epsilon naught, sorry, I said this is epsilon naught, sorry, times the quantity V naught over 3 capital R plus 2V naught over capital R P sub 2 times cosine theta. Okay, so that's all for that one. Moving along now to number 6. Okay, so for number 6, let's see what we have here. For number 6, a parallel plate capacitor has plate area A, separation D, and free charge plus or minus Q. The lower half of the space between plates is filled with dielectric constant kappa, while upper half is vacuum. Okay, A, B, C, D, E, respectively, find the electric displacement field D, find the electric fields in both regions, find the potential difference between the plates, find the capacitance, and find the bound surface charge densities in the dielectric. Okay, so this is a capacitance with dielectrics problem. So what we could do here, free charge D equals Q over A, so D equals Q over A and hat. Our potential difference, V equals E sub VAC, D over 2 plus E sub DIEL, D over 2. And this is series configuration geometry here. Our capacitance here, C equals Q over V equals 2 kappa epsilon naught A over D times the quantity kappa plus 1. In vacuum, E sub VAC equals D over epsilon equals Q over epsilon naught A. In dielectric, E sub DIEL equals D over kappa epsilon equals Q over kappa epsilon A. So V equals QD over 2 epsilon A times the quantity 1 plus kappa. And from here, our polarization, our P equals epsilon naught times quantity kappa minus 1 E sub DIEL. So P equals kappa minus 1 over kappa times Q over A. And our sigma sub B equals plus or minus P. Okay, moving along to number 7. Okay, so number 7, a uniformly charged solid sphere of radius capital R has total charge Q, A, B, C, D respectively. Find the electric field everywhere. Compute the total electrostatic energy using U equals epsilon naught over 2 to integrate and the integral E squared D tau. Sorry about that tau. C, compare the compare this energy with the energy of a thin spherical shell of radius capital R, total charge Q. Which configuration has lower electrostatic self-energy? So electrostatic energy problem. Energy of uniformly charged sphere. The electric field, well, inside E is 1 over 4 pi epsilon naught times QR over capital R cubed. Outside E equals 1 over 4 pi epsilon naught times Q over R squared. Our energy, U equals epsilon naught over 2, and the integrated this E squared, this integral d tau. The inside contribution, use of N equals Q squared over 40 pi epsilon naught R. Our outside contribution, use of out equals Q squared over 8 pi epsilon naught R. Our total, U equals 3Q squared over 20 pi epsilon naught R. For a thin spherical shell, U sub shell equals Q squared over 8 pi epsilon naught R. And we can conclude here, since 3 over 20 is less than 1 over 8, the uniformly charged sphere has lower self-energy. Okay, so moving forward to number 8. Okay, so for number 8 here, we have a conducting material fills the region between the concentric spherical shells of radii A and B, respectively, with B is greater than A. The conductivity varies as sigma of R equals sigma naught times A over R. So a potential difference V naught is applied between the inner and outer shells. All right, A, B, C, D. Okay, find the current density J of R, find the total current I, find the effective resistance between the shells, and find the power dissipated in the material. So this is a spherical resistor problem. Okay, the current is radial, so I equals J of R, 4 pi R squared, and Ohm's law, J equals sigma times E. Our resistance, dr, equals D lowercase r over theta over sigma of lowercase r 4 pi lowercase r squared. Our r sub EFF equals the integral from A to B of dr over 4 pi r squared sigma naught A divided by r. So this is going to be 1 over 4 pi sigma naught A integrated from A to B dr over r. So our r sub EFF, when we integrate this, this becomes, 1 over 4 pi sigma naught A times log B over A. Current I equals V naught over R E sub FF. That equals 4 pi sigma naught A V naught over log B over A. Current density J of R equals I over 4 pi R squared, and our power P equals I V naught. Well, that's going to be V naught squared over RE sub FF. Okay, so moving along to number 9. Okay, so number 9, a long solid cylindrical wire of radius R carries a steady current density. J of R equals J naught times the quantity 1 minus R squared over capital R squared Z hat. For R is less than or equal to capital R, find the total current I, find the magnetic field B of R inside the wire, find B of R outside the wire, determine where inside the wire the magnetic field is largest. So this is a magnetostatics and Ampere's law problem. So the magnetic field of a non-uniform wire, J of R equals J naught times the quantity 1 minus R squared over capital R squared. So here for part A, total current I equals the integral of J dA. I is going to equal 2 pi J naught from 0 to R, integrated from 0 to R. Quantity 1 minus R squared over capital R squared, lowercase r dr. So after doing that, performing the computation, I equals pi J naught R squared over 2. Okay, part B, for R is less than capital R, I sub E and C equals 2 pi J naught times the quantity R squared over 2 minus R to the 4th over 4 capital R squared. By Ampere's law, B of 2 pi r, that's going to be equal to mu naught I sub E and C. And here, B of r equals mu naught J naught times the quantity r over 2 minus r cubed over 4 r squared. Okay. And for r is less than capital R, B of r equals that mu naught I over 2 pi r equals mu naught J naught r squared over 4r. And our maximum inside, I'm going to take that derivative of B with respect to r, set it equal to 0. And that's going to be 1/2 minus 3r squared over 4 capital R squared equals 0. Solving for lowercase r, we're going to get lowercase r equals capital R times the square root of 2 over 3. Okay, so that's number 9. Moving along to number 10. Okay, so from the same current distribution in problem number 9, choose a convenient gauge and write A equals A sub z r z hat. Find A sub z of r inside and outside the wire. Make A sub z continuous at r equals capital R and verify that the magnetic field at B equals the cross product of del and A. So vector potential problem. So choose for A equals A sub z of r z hat. Then B sub phi equals negative d A sub z dr. So that derivative there. Inside this negative d A sub z dr, that equals mu naught J naught times r over 2 minus r cubed over 4r squared. So we integrate this, we get A sub z equals negative mu naught J naught times the quantity r squared over 4 minus r fourth over 16 r squared plus c. And then from here, outside negative d A sub z dr, that equals that u naught I over 2 pi r, A sub z equals negative mu naught I over 2 pi log r plus c prime. So constants are chosen, so A sub z is continuous at r equals capital R. Gauge freedom means the additive constant is arbitrary. Okay, number 11. Okay, a circular loop of radius r carries current I, A, B, C, D, E. Find its magnetic dipole moment. Write the far field magnetic vector potential. Write the far field magnetic field. Find the torque on the loop and uniform external field B sub naught. And find the potential field in the loop in B naught. Okay, magnetic dipoles problem, going through this quickly. This is a condensed version. Magnetic dipole moment, that's equal to I pi r squared n hat. Our far field vector potential A equals mu naught over 4 pi times the cross product of m and r hat over r squared. And our far field magnetic field B equals mu naught over 4 pi r cubed times the quantity 3 times the dot of m and r hat minus m. And our torque, that's going to be that tau, that torque equals the cross product of m and B naught. And potential energy U equals the dot product of negative m and B naught. Okay, so that's for number 11. Moving along to number 12. Okay, so 12, a circular loop of radius A and resistance R lies in the xy plane. A spatially uniform magnetic field points in the z direction and varies as B of t equals B naught e to the negative t over tau. A, B, C, D, E respectively. Find the magnetic flux for the loop. Find the induced EMF. Find the induced current as a function of time. Determine the direction of the induced current. And E, find the total energy dissipated in the resistor from t equals 0 to infinity. So this is Faraday's law. Our flux here. Okay, our phi sub B equals B of t equals B of t pi a squared. And that's going to be our phi sub B equals B naught e to the negative t over tau pi a squared. Okay, our induced EMF, that's going to be a negative, the derivative here, negative d phi sub B dt, and that's going to equal that B naught pi a squared over tau e to the negative t over tau. our current. I of t, well, that's going to wind up equaling this b naught pi a squared over r tau times e to the negative t over tau. And since b in positive z hat is decreasing, the induced current produces a positive z hat field. Therefore, the current is counterclockwise viewed from positive z. For the energy dissipated, U equals the integral from 0 to infinity, I squared R dt. U equals 0 to infinity now, substituting this is going to be B naught squared pi squared a to the fourth R tau squared times e to the negative 2t over tau dt. And then performing the operations, we get U equals B naught squared pi squared a to the fourth over 2R tau. Okay, that's all for part 1 through 12. Part 2, 13 through 18 is next. Thank you very much. And my apologies if I mispronounced anything. Thank you.